I had a question from section 12.04 on the piecewise function and how that represents recursion and how the final answer is determined. So I thought I would take a minute to go through that and start using some of the key vocabulary words that you're going to be hearing and reading a lot about in recursion. So in section 12.04, they talk about this piecewise function as an example of recursion. So recall, or as you are learning, a recursive definition consists of two things. A recursive case, which is the top item here, f of x minus 3 plus 2, when x is greater than or equal to 10. And then also something called a base case, a non-recursive part. This allows us to escape from recursion. So I'm going to work through an example to show you why this piecewise function is in fact recursive and how you generate the answer. Now, in the body of the information in the lesson, they go through this, but I'm basically going to put my own spin on it and provide you with some audio explanation. So this is what you start with. Let x equals 20. So just ignore this part at the end. X is 20. So we take 20, we plug it in for x. So inside the piecewise function, since x is greater than or equal to 10, we're going to use this definition. So we plug in 20 for x. So f of 20 minus 3 plus 2, I simplify this and I get f of 17 plus 2. Well, looking back on my recursive definition, if this is 17, 17 is greater than or equal to 10, so I'm going to need to call the function again, but this time instead of x equaling 20, it's going to be 17. So then I start the process again. So I'm using the recursive part of the definition. So in other words, the function calling itself with a reduced value inside of the parentheses. So it's like we're starting again. F of 17, I use the recursive part. I plug in 17 for x. 17 minus 3 is 14. So I have f of 14 plus 2. So 14 is still bigger than 10. So I'm calling the function again. So watch my arrow. So it's like I'm starting over. Another call to the function. But this time, the value of x is 14. 14 is still bigger than 10, so I'm going to use the recursive part of the definition again. I plug in 14 for x, and I simplify. 14 minus 3 is 11, and then we have the plus 2. Once again, 11 is still greater than or equal to 10, so I'm going to call the function again, which I'm showing here, with x equal to 11. 11 is bigger than 10, so I'm going to use the recursive part of the definition again. So I plug in 11 for x here, and then I simplify. 11 minus 3 is 8, so I have f of 8 plus 2. Now, this time, 8, when I look at my piecewise function, 8 is less than or equal to 10. So finally, I can use the base case of my function, the non-recursive part. So that means f of 8 is equal to negative 5. So now, this is how the answer is derived. And when you're working with recursion, the best rule of thumb is to go back to where you were called. So we plug in negative 5 in for f of 8, and we simplify. Negative 5 plus 3 is negative 3. Now, I go back to where I was called. I was called from, how did I get here? I got here by calling f of 11. So I go back to where I was called. So in place of f of 11, I plug in negative 3 because f of 11 was equal to negative 3. So I come up here, negative 3 plus 2 is negative 1. So negative 1 is really what f of 14 is equal to. So I go back to where I was called, and f of 14 was called right here. So I take negative 1, I plug it in for f of 14. And then I simplify. -1 plus 2 is 1. So that means f of 17 is equal to 1. I plug that in to where f of 17 was called right here. I go back to where I was called. So I plug 1 in for f of 17. 1 plus 2 is 3. So that means f of 20 is equal to 3. And that's how I arrive at the answer. So again, a piecewise function is made up of a recursive case and a base case. And then for a given value of x, these two parts of the definition of the piecewise function work together to generate an answer.